Hey everyone, welcome back to Bug no Jutsu. If you're someone who's working hard to crack LeetCode problems and grow stronger in DSA, you're in the right place. Today, we're diving into a deceptively simple problem that requires both intuition and a sharp understanding of sliding windows. We're talking about LeetCode problem number 3487, maximum unique subarray sum after deletion. Let's break it down and understand how to approach it like a pro. You are given an integer array called nums. Now here's the twist, you are allowed to delete any number of elements from the array. Yes, any number of them, but you cannot make the array empty. At least one element must remain. After doing these deletions, your task is to select a subarray, and remember, a subarray means a contiguous segment of the array. This subarray must follow a specific rule. All the elements in it must be unique. Your goal is to find such a subarray with the maximum possible sum. So, delete whatever you want, but from the remaining array, choose a contiguous piece that has all unique values, and make sure that the sum is as large as possible. Let's take a moment to break down example 1, where the input array is nums equals 1, 2, 3, 4, 5. Now, the first thing we notice is that all the numbers in this array are already unique, none of them repeat. That's important, because one of the conditions of the problem is that the subarray we choose must contain only unique elements. In this case, the entire array already satisfies that condition. Next, let's think about deletions. Remember, the problem says we can delete elements, but we don't have to. So we ask ourselves, if we deleted any of these numbers, would it help us? The answer is no. All of them are positive, and deleting any number would only reduce the total sum. So there's absolutely no benefit in removing anything here. That means the smartest move is to keep the array exactly as it is and simply select the entire array as our subarray. Since it's already contiguous, already unique, and contains only positive values, it's perfect. When we add everything together, 1 plus 2 plus 3 plus 4 plus 5, we get 15. And that's the maximum sum we can possibly achieve under the given constraints. This example serves as a great sanity check for our logic. When the input is already ideal, our algorithm should be able to recognize that and return the full sum without overthinking it. In this solution, we begin by creating an empty set to collect all the positive unique numbers from the input array. As we iterate through each element in the array, we check if the current number is positive. If it is, we add it to the set, ensuring that only unique values are stored. At the same time, we keep track of the maximum value among the negative numbers. This is important in case the array contains only non-positive values, where no positive subarray can be formed. In such scenarios, the best possible answer is simply the maximum single value present in the array. Once we finish scanning the array, we check whether our set of positive numbers is empty. If it is, that means the array had no positive values at all, and we return the maximum negative number we tracked earlier. Otherwise, we move on to compute the total sum of all unique positive values stored in the set. Since the set guarantees uniqueness, we don't have to worry about duplicates. Finally, we return this sum as our result. The underlying idea of this solution is that when dealing with an array that may have duplicate or negative values, we are allowed to delete any number of elements to form a subarray. So, the best possible outcome in many cases is to pick all unique positive numbers from the array, essentially treating them as if we've deleted all other elements, and return their total sum. If the array contains only negatives, then we simply return the least negative number, which is the maximum possible sum we can achieve in that case. In terms of time complexity, this solution runs in n time, where n is the length of the array. That's because each element is added and removed from the window at most once. The space complexity is also n, in the worst case, due to the set we use to track which elements are currently in the window. This problem is a great example of how understanding the constraint unique elements in a subarray naturally leads us to the sliding window technique. It also teaches a valuable lesson. Sometimes you're allowed to delete things, but the optimal result might already exist in the original array. Also, This problem is similar in spirit to other popular ones like maximum erasure value or longest substring without repeating characters. If you've solved those before, you'll feel right at home with this one. In competitive programming and interviews, problems like this test your ability to maintain a moving window under constraints, and being able to code this efficiently is a skill that pays off again and again. Alright, that's a wrap on this one. If you found this explanation helpful, drop a like, hit subscribe, and share it with a friend who's grinding through LeetCode just like you. And hey, if you want the same problem broken down visually with dry runs and illustrations, let me know in the comments. I'm always listening, always here to help. Thanks for watching, this is Bug No Jutsu, and I'll see you in the next one. Until then, keep coding, and keep getting better.